Good afternoon, everybody. Welcome to Thursday afternoon at Chem 1105 with your host, me, Dr. White. Hi, everybody. Don't forget, the deadline today is until 4 p.m. to get test number 2 in. By Sunday or earlier, I will have your scores for test number 2 in Blackboard. I'll send out an email by that time or sooner. I'll also send out an individual email to each of you with the points for each answer on test number 2. Next Monday, I will go through test number 2 answers, but I'll cut it out of video. I like my special effects. Cut it out of video, and I will post it as a private video, and I'll send out an email with the URL so you can view it if you're not here live to see me go through test number 2 answers. All right, let's go to the lab, and then we'll go on to coursework. Now, today's lab is molecular models and VSEPR. Now, the reason I'm here is I want to show you the following notes that's important. In this lab, only do the following molecules. You'll see what I'm talking about: methane, water, ammonia, chloroform, hydrogen sulfide, formaldehyde, dichloro-difluoromethane, otherwise known as Freon, and hydrogen cyanide. Also, you do not have to fill in the polar, non-polar, polar column in the last chart. Also, for this lab, no selfie is needed. Now, this is a lab one of the other faculty members made up dealing with molecular models and VSEPR. Unfortunately, you don't have any molecular models, but you can do it anyways. When we do it face-to-face, I hand out the models, but you don't need them. They're nice, but you don't need them. Let's talk about VSEPR. The answer is yes, you do have to give the shape. And I'll explain now how to do that. Now, can everybody see? And I hope you can. I can check now. This is something they just added to Zoom about 3-4 months ago, where I can check to make sure what I think you're saying, you are saying, before I'd have to ask the class. But anyways, on your screen, you see the Wikipedia entry for VSEPR, VSEPR theory. I'd highly recommend you look at this before you do the lab. I'll say it again. You know what I can do? Hold on. I don't know why I didn't do this before, but I'm doing it now. There you go. The link to what I'm going to show you will now be in the lab. Let's find out. Go to student view. And you'll see here, please read the following before doing the lab. Let's go to the following. All right, now, VSEPR stands for valence shell electron pair repulsion. That's what it stands for. And this is a way of predicting the geometry of molecules. Molecules don't exist flat. They, like my hand or you or me, they exist in 3 dimensions, X, Y, and Z. Now, the reason it's called valence shell, because you're talking about the outermost electrons, the valence electrons, and they're in shells, as you know, all electrons are, and electrons exist in pairs. And this talks about how the electrons, both the bonding and non-bonding, want to be as far apart as they can, not close together, far apart as they can. And they talk about repulsion. Now, if you scroll down and look where it says main group elements, it has the molecule type, what it looks like, and the geometry. Now, if we look at E is the non-bonding pair of electrons, X is the number of atoms attached to the central atom. So let's look at today's lab. All right, today's lab is this, and you have to answer some questions. Now, everybody should get number 1, what does VSEPR stand for? I just showed you. And we talked about in class, and you should have known this for test number 2, how many electrons are in a single bond? How many in a double bond? How many in a triple bond? And what are valence electrons? Now, this we've already done for test 2, write the Lewis dot structure for each, and I call it just the Lewis structures, but you are using, some people call it Lewis dot, for each of the following. Remember, Lewis structures are valence electrons. And when you do that, you put 1 dot on each side of the element symbol, chemical symbol, before you pair up. Now, here's the chart where I said you don't have to do all of them, but some of them. Go back and look at, like this one, phosphorus triiodide. Nah, I've never used it. You're never going to use it. But for this one, let's look at methane, CH4. Methane is also what you call natural gas. If you have a natural gas oven and stove, guess what? You're burning this to make the heat to cook with. Well, what's the Lewis dot structure? Well, we went through this, and I'll do this one for you so you can see what you have to do for this lab. But first, I have to open up my periodic table. Oh, and I also have to turn on my tablet. Well, while we're waiting for my tablet to, it's now running. All right. Now, you have to, for that table, draw the Lewis structures. Oops, I almost did something I haven't done in this class because none of you can read cursive. And each one you have to draw the Lewis structure for the following molecules. Now, methane has 1 carbon and 4 hydrogens. And as soon as you see the word Lewis, you should think of valence electrons. And I did, and hopefully you did. Well, we have to find how many valence electrons does hydrogen and carbon have. Well, you look for the chemical symbol H, hydrogen. Look at the top of the column in red. 1 tells you 1 valence electron. If we look at carbon and we look on the top, it has 4 valence electrons. So carbon has 4 valence electrons. Got ahead of myself. Hydrogen has 1 valence electron. But remember, there are 4 of them. So the carbon is here, and you've got a hydrogen here. And you didn't know, but atoms can talk to each other. No, they can't, but it sounds nice. Oh, Dr. White made it funny. But anyways, this hydrogen says to this carbon, I have an unpaired valence electron. You do. Let's share. And they do. And the second carbon or second hydrogen carbon does the same thing. 1 valence electron, 1 of the 4 here, and the next one does the same thing. And the last one does the same thing. So here's the Lewis structure for methane. Everybody better get that one right. Now, the next question, if we look at that chart, is the molecular shape. How do I do that? Good question. Remember, polar, nonpolar, don't do. Ah, that was easy. So how do we get the molecular shape of methane, CH4? Well, you look at the main group elements in this Wikipedia, which I put the link, the VSEPR theory. Now, methane has 4 hydrogens and a center carbon. Think of the A here as carbon and each X here a hydrogen. And if we look here, that's the molecular shape. It's tetrahedral. And tetrahedral looks like this. Each one of these balls is a hydrogen, and the, I guess, pink color or chartreuse, whatever, pink color in the center, wine color, phenolphthalein when you add base to it, and nobody understood what I just said. But the center here, colored center, is the carbon, and this is tetrahedral. And that's the actual shape of the methane you burn. So in this table right here, running out of room, sorry, you'd put tetrahedral. And here, you would put the Lewis structure for methane. And you have to do those for the rest listed on here. Let's look at one more and I'll give you a head start. Water. And I think you all know water is a good thing because it keeps us alive. Oops, that's not what I want. That's what I want. Now, water, you have to find, first of all, you need to do let me go back one, find out how many non-bonding pairs of electrons and how many atoms are in water. Now, I'll give you a hint. Water has 2 hydrogens going to an oxygen, and it has 2 non-bonding pairs of electrons. In this chart, E is non-bonding pair of electrons, and X is hydrogen or any other atom. And the center A is the center atom. For water, it would be oxygen, and the X would be hydrogens. Now, you've got to find on this table, and they've got a prettier one down here, where they show you what it actually looks like for different types of geometry. But I would stick to this table. I'll give you a hint. I would stick to the number 4. And that would help you find everything on there. And that's lab we're doing today. Answer all these questions, fill out this table, do the Lewis structure for these elements, and you're done. Any questions? Well, in that case, let me close something. And let's get to work. Oh, yeah, before we get to work, I have to open up a few more things. All right. Yesterday, I taught you the ideal gas law, PV equal nRT. We went through 2 problems. On Monday, I'll go through another one, because on Monday, I will go through Chapter 6 practice problems, which include this. But let me remind you something about PV equal nRT. And PV equal nRT tells you when you really should look at your car tires. In the winter, what happens to the temperature? T is temperature, and PV equal nRT, it goes way down. Now, PV equal nRT is a gas law. That means this side is always equal to that side. The word law tells you it's always true, period. No exceptions, or it wouldn't be a law. So in the winter, you have PV equal nRT. Now, in your car tires, the volume, the number of moles N, and the universal gas law constant R are always the same. So if the temperature goes down, then the only thing that can change on the left is the pressure, and that will go down. So in the cold of winter, PV equal nRT tells you temperature goes down outside, the pressure in your car tire will go down. By the way, I should have a little subtle hint here. We get the hint? Know this. How does PV equal nRT show you when to test your tires? And again, PV equal nRT tells you when to check your tire pressure. Now, this is for in the winter. How about in the summer, where we are now? And what happens in the hottest part of the summer? And unfortunately, if you were in Arizona now and other places, Southwest and even Southeast, the temperature goes way up. In fact, hold on, somebody had that high. Someone check. Well, let's take a quick look. Wrong screen, right screen. This is my favorite weather site, Weather Underground. I did have it right. If we look at, that's not what I want. I didn't know there was a Phoenix. Well, let's go to Arizona City, Arizona. And if you look at the temperature, it's 108 right now. Ouch, 108. Now they say, well, it's dry humidity. It's not as bad as high humidity, but it's still pretty bad. I've been in towns in Arizona when it was hot and you still felt hot, even though the humidity is low. Well, if you were in Arizona right now, the temperature is way up. Let's even go like this, way up. And PV equal nRT. Remember, in your car tires, the volume, the moles, and the universal gas law constant R stay the same. If the temperature goes up and both sides of this equation have to remain the same, then the only thing on the left that can change is the pressure, and it will. Boy, I'm glad I'm not down there right now. Feel sorry for those people. All right, let's move on. We did our ideal gas law practice time, and let's talk about Dalton's law of partial pressures. Now, Dalton is a great English chemist, and he came up with this law that the total pressure exerted by a mixture, and this should be a gas mixture of gases, is the sum of the partial pressures of the individual gases. What's a partial pressure? Oh, look right here. And that is the partial pressure is the pressure that a gas and a mixture would exert if it were alone under the same conditions. So if you have a mixture of gases like what you're breathing now, each individual gas has what we call a partial pressure. And that's what the pressure would be if it were alone and not in the mixture. And Dalton's law is the total pressure, P total, is the sum of all individual partial pressures, P1, P2, P3. And the reason I have N, if it was 5, then you'd have a P4 and a P5. If we're 8, you have 1, 2, 3, 4, 5, 6, 7, 8 partial pressures. I'll be done in about a half hour. No, this is a lot to write. I just thought something I could type it quicker. All right, I did it. I finished. I should get a point just for reading all of this. Anyways, if a mixture of oxygen, O2, and nitrogen gases has an oxygen partial pressure of 251 torr and a nitrogen gas partial pressure of 510 torr, then what is the total pressure of the mixture? And as I've taught you, what are you being asked to find? The total pressure, which we abbreviate by P total. What are you given? Somebody already beat me to the answer. You're given the partial pressure of oxygen. And we show that by this. PO2 partial pressure is 251 torr. And then the nitrogen partial pressure is equal to 510 torr. And now the question is, how do you solve this? Well, as soon as you see the word partial pressure anywhere, you should think of Dalton's law of partial pressures, which reminds me, I better open up something else. And on your screen, you can see Dalton's law of partial pressures. The total pressure, P total, and you can abbreviate it sometimes P tot, which I did. I'll put the AL in a second, not to confuse anybody, is the sum of the partial pressures. Again, this is another thing in the past students would have to memorize. You don't. So P total equals the sum of the partial pressures. Well, we've got two of them. Partial pressure oxygen, partial pressure nitrogen. And that's 251 torr plus 510 torr. And if you add them up together, we get 761 torr. And that's how you use Dalton's law of partial pressure. Oh, let's do another one. All right, let's take a look at this one. If a mixture of argon, that's Ar, and nitrogen gases, N2, have a total pressure of 800 torr, and the partial pressure of argon is 200 torr, then what is the partial pressure of nitrogen? Guess what? I'm going to let you try this all on your own, but I will tell you that you can find an important information Dalton's law of partial pressure. And it's your turn to try it all on your own. I see one person already got it right, but we'll give everybody time to finish. And also, Dr. White, time to get some water. All right, my turn. What are you being asked to find? What is the partial pressure of nitrogen? Pn2. What are you given? Up here has a total pressure of 800 torr. So P total equals 800 torr. And I think this is the only time we're going to do subtraction. And you know the partial pressure of argon is 200 torr. Now, as soon as you see the word partial and the word pressure, you should think of Dalton's law of partial pressures. The total pressure equals the sum of the partial pressures. In this case, P total equals partial pressure of nitrogen plus the partial pressure of argon. Doesn't matter which order you put one or the other first. Now, what are we being asked to solve for? This. Well, we got to get rid of this. And how do you get rid of something when you're adding things together? A minus A equals 0, meaning that's gone. So if I subtract, I want to get rid of this because I'm trying to solve for partial pressure nitrogen. So I will subtract partial pressure of argon. Well, whatever you do to one side, you have to do to the other. This cancels out. So I have partial pressure of nitrogen equals P total minus the partial pressure of argon. Now I'm going to rewrite it because I like to do this. You don't have to. All I'm doing is rewriting it this way. It's the same thing. And now put the numbers in. P total is 800 torr. P argon, partial pressure of argon is 200 torr. And I don't need my calculator. I can do this one in my head. And the answer is 600 torr. And that's Dalton's law of partial pressures. And it's a useful thing like learning about how one gas, what's the pressure, and you can isolate it and find out how it reacts like if it were alone. Now, if I scroll down, oh no, we're done with this chapter. By the way, if you haven't figured out, if you look in the lower left-hand corner, you see page 28 of 28 right down here. That means we're done with this chapter. All right, on Monday, things are moving quick because a week from today, I believe, will be test number 3. End of the semester gets quicker, and we're getting there. So things are getting quicker. On Monday, I will do the problem set for chapter 6. On Wednesday, I'll do the next chapter, chapter 5, part 2. On next Tuesday, I will do the review for test number 3. Tomorrow, I will send out an email and post important information about test number 3. All right. Well, think about what we've done so far this semester. We've learned about chemistry. We've learned about important things with numbers, significant figures. We got into molecules, atoms. We talked about electronic structure. Then we talked about larger quantities, moles. And I just finished talking about gases. Well, we talked about gases. Let's talk about something liquids are involved in and other things too. And that is chapter 5, part 2, solutions. And solutions play an important part in our daily life. Now, what is a solution? It's a mixture in which one substance is uniformly dispersed in another substance. Another way of saying that is a homogeneous combination, that means it's the same throughout, of 2 or more substances in which each substance retains its own chemical identity. And this is a solution. Now, let's just real quick. An example of the solution is the air you're breathing. It's a mixture of oxygen, nitrogen gas. And the oxygen is what keeps us alive, but the nitrogen is important too. Now, here I'm sitting, breathing, still alive. That's a good thing. And if I walked over to that door, which I'm not, but assume I did, I wouldn't go, I can't breathe. There's no oxygen. No, it's uniform. Here is the same amount of oxygen than by my door. Or if I go downstairs in my living room, that's because the air you breathe is homogeneous solution. It's a solution. Now, I'm not going to do it, but there's water in here. And if I were to take some sugar and shake it up like this, it would look the same throughout. It'd be homogeneous. And that would be a solution of sugar and water. And it would be the same. Now, I could very carefully remove all the water, and what would be left behind? The sugar, because neither of them react to make something new. And you could do the same with salt and water, even though I wouldn't be drinking. Well, yes, you do. They call it Gatorade. So a solution is a homogeneous mixture of 2 or more substances. Now, when we talk about solutions, there are 2 things you should know. Oh, it's subtle time. Subtle? And know this. And we talk about solutions. They contain a solvent, and a solvent is the component of the solution present in the greatest amount. And the other components are called the solutes. Now, a solute is a solution component that is present in a small amount relative to the solvent. So in a solution, you can only have one solvent, but you can have many solutes. And if we think about it, the air we breathe, that's not what I want. This is what I want. The air we breathe, let's assume you had 100 grams of air. Air is composed of every 100 grams, 20 grams oxygen, approximately 80 grams nitrogen, which is to say is 20% oxygen, 80% nitrogen. And what is the solvent of air? Well, it's the component present in the greatest amount. And which is greater, 20 grams or 80 grams? And hopefully all picked 80. So in air, nitrogen gas, N2, is the solvent. And oxygen gas, O2, is a solute. Again, solvent, the component present in the greatest amount. Solute, all the other components. I think a lot of you have in your house rubbing alcohol. I know I have it, and they have different types now. And a common type is 70% or 70 grams alcohol, isopropyl alcohol, which is abbreviated IPA for people who work in the chemical industry. I have, and 30 grams of water. And the question is, in rubbing alcohol, what is the solvent? What is the solute? Your turn to have some fun. I'm going to share the fun today. Remember, the solvent is the component present in the greatest amount, and the other components are called the solute. Somebody already got it right. Again, everybody's done. And which of these is present in the greatest amount? And the answer is isopropyl alcohol, abbreviated IPA, and that's the solvent. And here, water would be the solute. Now, in many things in our life, water is the solvent. But as you see in rubbing alcohol, it doesn't always have to be the solvent. Let's do one more. These are fun. Oops. Now, Dr. White loves his vodka. The best stuff is something like Grey Goose or Absolute. But if you go to Costco, they're what they call their French vodka is just about the same as Grey Goose or Absolute, and it's a lot less money. I didn't say that. And I'm not in any way suggesting you purchase or consume any alcoholic drinks. But in vodka, you have 40 grams of ethanol. That's the molecule. When you consume too much, you get inebriated. And it has 60 grams of water. In vodka, what's the solvent? What's the solute? I could have 3 or 4 points in this solution. What's the solvent? What's the solute? And I see people are getting the answers correctly. Thank you, Judith. Thank you, Julia. All right. So the question is, what is the solvent in vodka? And it turns out the compound present in the greatest amount, 60 grams is greater than 40 grams, water is the solvent in vodka. And the ethanol is the solute. Wow, we were having so much fun. I didn't realize it's time to take a 5 or 6 minute break. I'm going to get up and stretch. I'll see you in about 5 minutes or so. I'm going to get up and stretch. Time to get going. All right. I was talking about solutions. And we talked about how in a solution, the solvent is the component present in the greatest amount. And the other components that are present in smaller amounts relative to the solvent are called the solutes. Now, when we talk about solutions, most people think of solutions being liquids, but it doesn't have to be. The air we breathe has a solution that contains nitrogen, oxygen, and also, I didn't mention earlier, has water vapor, water in a gas form. Now, liquids can be very complex solutions. The pop you drink, by the way, Dr. White was born and raised in the Chicagoland area. I spent most of my life here in the Chicagoland area, by Chicago in the suburbs, except for the 5 years that I was at Michigan State in East Lansing, Michigan, getting my PhD. And the liquid we drink that's non-alcoholic in a bottle or a can, we call pop. You're on the East Coast, you call it soda. Oh, let me share something personal with you. And if you see on your screen, my all-time favorite pop is Dr. Pepper, and this one, Werner's. Now, Werner's is a very spicy, highly carbonated ginger ale. I love it. I have a couple of these cases right here in my home right now. And I really like it. I also love Dr. Pepper. I have some of that in my house. I also like uh, cream soda, but I like these better. And the best place to buy Werner's, at least in my neighborhood, and I think most of them, is at a Jewel. Not that I get any kickbacks from Jewel, but you can always find Werner's there. And Werner's pop, now how when you pour a glass of pop, you see all those bubbles? That's carbon dioxide, CO2. And that's dissolved in that liquid, like this 2-liter bottle. There's carbon dioxide in there, there's sugar, there's water. Pop is a very complex liquid mixture or solution. Hold on, I have an important message. No, I didn't know there was a cream soda Dr. Pepper. I'll have to try that. Thank you, Judith. All right, let's get back. I got sidetracked thinking about, ooh, cream soda Dr. Pepper. Uh-oh, I know where I'm going to have to go tomorrow. Jewel, and get some. All right, now, salt and water would be a solution. Now, another very complex liquid solution is the gasoline you use for a car. Next time you drive by a gas station, they're selling a very complex mixture. And later in the semester, I will talk about gasoline and when we get into organic chemistry. Now, you can also have solid mixtures or solutions. Example, brass is a mixture, sterling silver. This is sort of outdated. The mercury amalgam dental fillings are mixtures or solutions, but most people don't use, dentists don't use those anymore. All right, now, water is a solvent in many solutions, not all, but many. And it's a polar solvent due to polar bonds. Now, this is important. Hold on. Oh, come on. Should have been red. Let's try it again. Now, in water, and I'll use a line for a pair of electrons, and I won't put it into non-bonding electrons. This bond, because of the difference in electronegativities, and I already talked about this, but now you should know it, there's a slight negative charge. That's what this little delta means. Slight positive charge, same little delta. Negative on hydrogen, on oxygen, positive on hydrogen, same thing here. And if you have another water molecule, the same thing happens. And there's a slight attraction. It's called the Coulombic attraction. Opposites attract, and this is called the hydrogen bond. It's not a true chemical bond, but it's a weak force, but it's still enough to affect the nature of many things. And you should know water can hydrogen bond to other molecules like ethanol, like isopropyl alcohol. That hydrogen bonds, and that allows the two to make a solution. Now, I already said this, so it can hydrogen bond to ethanol and isopropyl alcohol, also known as isopropanol or 2-propanol. Now, switches off, click. In water solutions, you have hydration. That's the process in which forces are broken around the solute for the water ions, it's really water molecules, for the water and ions are surrounded by the water molecules. So if I were to take sodium chloride, which is really sodium cations and chloride anions, there's an ionic bond between the two. When you put it in water, this ionic bond is broken, and you have each ion, positive, negative, surrounded by water. And the slight negative charge does this, and you've got more water. It's not really reacting. It's called hydration. And the same thing would happen with the chloride anion. Again, click, switches off for this slide. Hold on, I got to do something very important. All right, I'd like to talk about the concept of like dissolves like. Now, like dissolves like is a rule of thumb. Can you see it's written on that? Oh, wait, it's on this thumb. What it means by a rule of thumb is it's true about 95% of the time, most of the time. It's not a law. A law, a law in chemistry or in any other science is always true. A rule of thumb, see a thumb, is almost always true, but not 100%. And the rule of thumb I'd like you to know, and know this, is like solutes are soluble in like solvents. And what does that mean? We talk about substances There are two types. We can, many ways of identifying substances, and one is by its polarity. And they're polar substances and non-polar substances. And in like dissolved like, polar solutes are soluble in polar solvents. And nonpolar solutes are soluble in nonpolar solvents. But when you try and mix polar and nonpolar together, they're not soluble. Now, let's talk about polar substances. And hint, you should know this still. What are things that are polar? The most polar thing we know in our universe is water. Next are salts, like sodium chloride, potassium chloride, sodium fluoride, salts. And another one are alcohols, like ethanol. Now, what are nonpolar? Well, one is air, and doesn't have to be liquid. Another one would be vegetable oil is nonpolar. Gasoline is nonpolar. Vaseline is also nonpolar. And I'll teach you later on, dirt and grease are nonpolar. So what does this mean, like dissolves like? Well, if I take water and salt and mix them together, both are polar. Like dissolves like tells us they will be soluble. Now, if I take vegetable oil and Vaseline, guess what? It will be soluble. Now, years ago, I taught this in a Chem 1211 class. I had a really sharp student. I've had a lot of sharp students. And I just said that. And he said, and I hadn't said what I said about vegetable oil and Vaseline. Oh, one other one I forgot. Let's take air off here because that might confuse you. Baby oil is also nonpolar, and you should know this chart. And in the class, I just said nonpolar, polar, you mix two together, they won't be soluble. However, if they're both nonpolar or both polar, like dissolves like, they'll be soluble. And he said, Dr. White, if that's true, if I take some Vaseline and vegetable oil, will the Vaseline, which is a semi-solid, be soluble in the vegetable oil, which is a liquid? I said, well, like dissolves like, it's a rule of thumb. So there's about a 95% chance. Yes, it's true. In fact, if you don't mind, next lab, this is when we were face to face, if you don't mind doing it in front of the class, I'll give you some vegetable oil and Vaseline, mix them together and see if it's soluble. And he did. And it was, because like dissolves like. Now, if you see on your screen, I don't get a kickback from this company. My mother, when she was alive, God bless her soul, loved wishbone Italian dressing. Turns out I learned you later on how to make your own much better than that, but it's pretty good. And if you look at this bottle, you'll see there are two layers. A top one that is a light color and this darker layer that's on the bottom. How come there are two layers? Well, oil vinaigrette dressing, which is what Italian dressing is mainly water and vegetable oil. Water is polar, vegetable oil is nonpolar. And that's why you see the two layers. The bottom layer here is water, and it's got other things in there to make it taste good. And the top layer is the vegetable oil. That's got a few seasonings in it that are soluble in that. And when you mix it up, put it on your salad dressing, on your salad, and it tastes good. Oh, I love a good salad. Caesar salad is my favorite. But when you put the bottle down, they separate. Why? Like dissolves like. And it says I would not abbreviate vegetable oil. I'd type out vegetable. All right, let's look at the problem 5 points. Compound A is soluble in water, but not soluble in vegetable oil. Is compound A polar or nonpolar? And how do you know this? Your turn to have a little fun. So I'll give you a little time to answer that, and then I will. Remember, like dissolves like. Water, alcohol, salts are polar. Vegetable oil, gasoline, baby oil are nonpolar. Oh my goodness, everybody's done. What do I know about compound A? Compound A is polar. How do I know that? Because like dissolves like, it's on the other slide. I know that because I know like dissolves like. And I know that water is polar, and because like dissolves like, polar things are soluble in polar things. That tells me compound A is polar. And because of like dissolves like, vegetable oil is nonpolar. Compound A is not soluble in vegetable oil. Therefore, it's not nonpolar, it's polar. And that's like dissolve like. Now, later in the semester, we'll be using like dissolve. Hold on, stay down. It doesn't want to stay down. There. Anyways, later in the semester, we'll come back to like dissolves like, because I'll teach you, are you ready for this? How soap works. You know, that magic stuff that gets your hands clean, or if you use detergent, get your clothes clean, or if you use dishwasher soap because your dish is clean, that uses like dissolves like to work. And it's really exciting. I'll teach you about that. But you just have to wait until we get into organic. That's in about this chapter, next chapter, and the following chapter. All right, so you should know this. Like dissolves like. Polar things are soluble in polar things. Non-polar things are soluble in non-polar things. And you should know water, salts like sodium chloride, alcohol are polar. Non-polar, vegetable oil, gasoline, baby oil, Vaseline, dirt and grease are non-polar. By the way, baby oil, why do you think people put baby oil on the bottoms of babies' bottoms to keep them from getting rash? Because it's non-polar and it keeps the water off the baby's bottom. Wow, we're getting into everything in this class, baby bottoms and everything. Boy. All right, switches off, click. You've probably heard of the term electrolytes. Those are solutes that separate into ions when dissolved in water. The reason they're called electrolytes is because they conduct electricity. Pure water, which you cannot get your hands on, either can I, ultra pure. Actually, at one company I could, but it's very rare. Water has ions in it. The water you drink, the water you get from your sink has ions in it, which is why you don't want to have electricity around when you use water, because you'll electrocute yourself. Now, when we talk about electrolytes, a lot of the things that separate into ions are salts. An important product that came along years ago is called Gatorade. And athletes drink this to help replenish the water they've lost by exercising, but also other things. And if you look here, it has things like sodium citrate, which is a type of salt, and it's got a lot of sugar in it too. And this would be an electrolyte. You're replacing it. Let's try one other. And if you look here, what are the 4 ingredients typical in sport drinks? Well, they have electrolytes right here. First of all, it's water. Then to make it taste good, they load it up with sugar or other types of sweeteners like fructose is, I'll teach you, part of sugar also, or type of sugar, and electrolytes and other stuff. And non-electrolytes, click, are things that don't separate into ions and don't conduct electricity. Example would be an alcohol. Now, when we mix two things together, an important concept is solubility. And that describes the amount of solute components present in a smaller amount that can dissolve in a given amount of solvent. And the solubility, by the way, switches on of a solute is the maximum amount of solute that will dissolve in a given solvent. If you put one more molecule, 1,000th of a gram more, and you're over the solubility limit, it won't be soluble. It will stay as a solid and float to the bottom. Now, I have sodium chloride from Wikipedia. I might have mentioned this, but I'll mention it again. Wikipedia has been so heavily policed by chemists with the right credentials, Dr. White is one of them, that it's been years since I've seen a major error in a chemical post in Wikipedia. The other stuff, well, I don't know about that, but chemistry, it's rare nowadays you'll find any kind of error. And the nice thing about different substances, chemicals that are found in Wikipedia, you scroll down and you look on the right side of the screen, you'll see identifiers, names, then we'll see properties. And if you look down, you'll see right here, solubility of water. And that tells me at 25 degrees C, which is essentially called room temperature, I can dissolve 360 grams of salt in 1 liter, that's per L, 1 liter, that's 1,000 milliliters of water. In ammonia, it's a lot less. In methanol, it's even less. Now, that was 360 per 1 liter. Now, sucrose, and I'll teach you this again later, but you don't have to know it now. That's what you call table sugar. And if we scroll down to the right, we see solubility in water is about, now here they should have had it in liters, it's about 2,000 grams per liter. So sugar is much more soluble in water than salt. But if you go 1 molecule over the solubility, it will precipitate. It will not dissolve. Wow, this is turning into Subtle Thursday. And know this. Now, when we talk about solutions, there are different names chemists use when we're talking about solutions. Now, the first one is a saturated solution. And a saturated solution contains the maximum amount of solute that can be dissolved under the conditions that which the solution exists. When you have a higher temperature solution, generally, not always, but generally, you can dissolve more solute in that. But whatever temperature, when you have a saturated solution, you can't put 1 more molecule in there. Now, a dilute solution is a solution that contains a small amount of solute relative to the amount of that solute that could dissolve in that solution. And one time, years ago, I was at a bar in Chicago, got one of my favorite drinks, a mixed drink. Back then, I think I was drinking Canadian Club and 7-Up. And no, I'm not an alcoholic, but I do like my alcohol. And I drank some, and I could hardly taste the Canadian Club. And I called the bartender over and said, hey, this is really a dilute drink. Why don't you pour some more Canadian Club in there? He was not happy. And I gave him a look that I wasn't happy. Then I left the bar with my friends because they were diluting, meaning not putting a lot of alcohol in their drinks. They were ripping people off. And that was a dilute solution. So a dilute solution contains only a small amount of solute present relative to the amount that could dissolve. Now, the opposite of that is a concentrated solution. And a concentrated solution is a solution that contains a large amount of solute relative to the amount that could dissolve, which is what that bartender wasn't giving us. Now, back when I was a kid, and even in college, and you can still buy it. You look on your screen and I don't get any kickbacks. You can go to the supermarket and buy concentrated orange juice. And this is a can that's frozen with some water, but most of the material, the juice of oranges. Now, they've taken out a lot of the water. And what you do to make this is, if I still remember, it's been decades, you take and put one of these cans in a pitcher, and then you put 3 cans of water. What you're doing is diluting it, making a diluter solution from the concentrate. Now, interesting thing, when I was in college, one of my fraternity brothers loved to eat made concentrated orange juice right from the can, frozen with a spoon. But he loved it. We would always be laughing when he would eat that. You really like that? Yeah, I do. We didn't, but he did. And that's, see where it says concentrated? This is a concentrated solution of orange juice. They've taken a lot of the water out. But you never thought I'd get into orange juice in this class. Now, something that's very important. Now, on these slides, you should know these, but this is one of the most important things you should know. What is an aqueous solution? An aqueous solution is a solution in which water is the solvent. Aqueous comes from the Latin aqua, water. Aqueous, water solution, which water is the solvent. And it's shown where you'll see bracket, A, Q, close bracket, and that stands for aqueous solution. And whenever you see this in a formula, and I'll talk more about it, that means water is the solvent. Aqueous solution, water is the solvent. Now, in organic chemistry, we also talk about non-aqueous solutions. That's a solution in which water is not the solvent. And usually non-aqueous tells you there's no water in there, but it's not always true. But you should know, aqueous solution, water is the solvent. Now, switch is off, but what factors can affect solubility? Well, whatever solvent you're trying to dissolve something in, what temperature you're at, what is the solute, what are other solutes present, and sometimes even the pressure around the solution. Again, switch was off. Now, switch, it's not, this is important, but I'm not going to put it on test. Oh. The effect of temperature on solubility, for most, but not all, well, all of them, solubility of a substance depends on the temperature. But for most solids, but not all, but most of them, about 90%, solubility increases as temperature increases. If you ever made a syrup solution for cooking, what do? You take water, you put a lot of sugar in there in a pot, and you heat it up and stir it until all the solid is gone. It dissolves. By heating it, that makes more of it go in, and it also dissolves quicker. Now, sometimes you look at something and say, oh, that's a solution. And the answer is it's not. Well, I'm really being subtle today. And if you look at a bottle of ketchup or mayonnaise, you say, oh, that's the solution. And it's not. It's what we call a colloidal dispersion. And a colloidal dispersion are small particles of one substance in another. Mixtures in which materials don't really dissolve, but are dispersed. Now, I'll never ask you what is a colloidal dispersion. And another thing I won't ask you is, instead of solvent and solute, we call the solutes the dispersed phase, and this what we normally call a solvent, but in a colloidal dispersion, we call that a dispersing media. Now, this is something you should know. You should know. How can you tell a hold on, I'm preparing a very special. Sorry about the delay. Now I'm ready. Bingo. All right. Now, how can you tell a solution from a colloidal dispersion, also known as colloids? And a colloidal dispersion disperses light pass through them. In other words, you cannot pass light through a colloidal dispersion. Now, how can we tell if it's a colloidal dispersion or not? All right, now, as you can see up here, if you don't know what that is, that's part of my collection of flashlights. I am a flashlight collector. And one of the best people who make flashlights in the world is a gentleman in China, Hank Wang. And here's one of his flashlights. They're the best, really. I think I've got about 15 Hank Wang. This is one of my favorites. And a white light, and this is adjustable. Wicked. Now, if I had sugar in here and it was a water solution, you see the white go through there. If I had ketchup in there, the light doesn't go through it. That's because ketchup is a colloidal dispersion. Same thing with mayonnaise. If you take a bottle of mayonnaise and put a light next to it like this, guess what? It won't go through. Not like this. Oops, sorry about that. Got it on low. A solution at will, a colloidal dispersion, because the particles stop the light, disperse the light from going through. You should know that. By the way, this is still one of my favorite lights. I'm not going to tell you they're not cheap, but oh, are they good? I have one of the lights up here will shine the distance about 8 or 9 football fields, almost a half a mile. All right, back to fun things in chemistry. Now, you should know what are examples of colloidal dispersions. One is milk. Milk is a colloidal dispersion. Another one is latex paint. That's a colloidal dispersion. And a third one, and do not try and take some blood and see if it scatters light. It will, but don't try it, is blood. Blood is not a solution. It's a colloidal dispersion. And you should know this. Now, how do chemists quantitatively describe solutions? If we're face-to-face in a lab, and I ask 2 students, here's some salt, here's some water, make me a salt solution. Well, they could mix different amounts of salt, each one, in different amounts of water. What if you want them always to be the same, or how would you describe that? Well, there are different ways how chemists describe the amount of solute present in a certain amount of solvent, and we call that concentration. And we call that concentration. I had to close some things. And there are 3 types of main concentration. One is percent concentration, and it's usually called by solids. Another one is percent by volume, and the one in red, the most important, is molarity. And you're going to have to wait. I'm going to do a cliffhanger. You're going to have to wait till Monday to find out about concentration, especially molarity. Do not miss Monday when I talk about molarity. It's important. Now, on Monday, I will go through, I'm looking at the clock, and it's about time, we're almost done. I will go through Chapter 6, Gases Problem Set. I highly recommend that over the weekend you work on that, because next week will be test number 3, which will be gases and solutions. On Monday, I'll finish up solutions, and on Tuesday, I'll do the review. On Wednesday, I'll go through the solutions problem set. Don't forget, hand in labs that are due. If you have any late labs, hand them in. You'll still get points. Don't forget, test 2 is due tomorrow by 4 p.m. Before you upload your PDF file of your answers, make sure your file contains all your answers. And with that, I'll say have a nice rest of the week and weekend. I'll see you on Monday. We get to talk about molarity. Ooh, it's going to be fun. And with that, I'll say gang gesund. Goodbye.